Hello, I'm Elaine Chan from Cheka Aikoza UTMKL, and I'm under the supervision of Dr. No Fatiha. The title of my final year project is Removal of Carbon Dioxide using Carbon Molecular Sieve as Adsorbent. Here are the key points of my presentation. I will start off with a comprehensive introduction of my research paper and the methodological approach. The presentation will end with a discussion of the data collected and also a conclusion. Greenhouse gases are the primary factor that contribute to global warming, particularly the emission of carbon dioxide by fuel combustion. Policymakers put the blame on CO2, which made up 80% of the greenhouse gases. The rising of sea level and the alteration in local climate are some of the obvious evidences of global warming. Therefore, prompt action should be taken to slash the rapidly growing anthropogenic CO2. Over the decades, several CO2 capture techniques have successfully drawn public attention. Based on available literature, physical adsorption using carbon molecular sieve (CMS) stands out as an effective method. Physical adsorption occurs when the gas molecules are held by physical forces like van der Waals force. CMS is a valuable material for the separation and purification of gas mixtures. Its microporous structure with less than 2 nanometers and enormous surface area are making it an ideal adsorbent. Nowadays, CMS is gaining popularity because of its fast adsorption rate, good thermal stability, and most importantly, it is possible for modification. Amine-modified adsorbent utilize the amine groups loaded to absorb CO2. The aminated adsorbent offered increased amount of reactive sites and high utilization efficiency of basic amine groups for acidic CO2 capture, leading to an enhanced CO2 capture capacity. Wet impregnation is the most common method used to prepare the amine-impregnated adsorbent. Polyethylamine (PEI) is the most common amine used out there, but in my paper, I employ diethylene triamine data and tetraethylene pentamine TEPA for CMS amine impregnation. Rapidly increasing concentration of CO2 in the atmosphere is worrisome. The traditional CO2 capture methods are mainly based on chemical adsorption with an aqueous solvent. However, these technologies are expensive and energy intensive. Today, adsorption using solid sorbent is considered as a modern yet effective technology. CMS adsorption is a contemporary technique that has been widely used in the petrochemical industry and become competitive to conventional separation process. A range of amide-modified CMS has been explored, as their increased surface basicity are favorable to enhance the CO2 adsorption capacity. These adsorbents were usually fabricated through loading amine by impregnation, particularly PEI. Therefore, a new research on removing CO2 by using CMS impregnated with data and TEPA should be integrated. Specifically, the study aims to accomplish the following. First and foremost, to modify the structural property of CMS with different types of amine. Next, to test the performance of CMS for CO2 adsorption. Last but not least, to determine the equilibrium isotherm models of CMS for CO2 adsorption. The experiment started off by preparing the commercially available CMS for amine impregnation. 2.6 grams of CMS was added to the isopropanol solvent and agitated. Then the mixture was poured to a round bottom flask containing 30 ml of amine solution as displayed in the image. After stirring, the solvent was dried in a rotary evaporator at 60 degrees Celsius for 5 hours. The textural property were obtained from nitrogen adsorption-desorption isotherms recorded at Quantachrome Novatouch instrument. The surface area, pore volume, and pore size were measured by using the multi-point Bronner and Merthaler BET method. Apart from that, the crystalline structure changes of the samples were investigated by X-ray diffraction (XRD) using a pananalytical and parent analyzer. In the next part of the experiment, the CO2 capture capacity were performed in a gravimetric sorption analyzer from Rubotherm instrument. The effect of operating pressure and amine types on CO2 absorption of CMS were both conducted using the same flow rate and operating temperature. The equilibrium absorption isotherm models of CMS were studied. The CMS can be now applied for removing CO2 from flue gas. The manipulated variables are the operating pressure and types of amine for impregnation. 7 operating pressure are chosen in the range of 0 to 30 bar to test the stability and capability of CMS under harsh conditions in industrial flue gas stack. The presence of amine groups conferred the basicity needed to capture CO2 molecule, which is categorized as Lewis acid. The prepared samples were denoted as CMS-X, where X represents the type of amines. For instance, CMS loaded with data is known as CMS-data. Turning our attention now to the result and discussion part. This table shows a distribution of CMS textural parameters from BET analysis. As compared to pristine CMS, both aminated CMS exhibit reduction in pore volume, surface area, and pore size. This is due to the addition of amine which might penetrate the framework of CMS and occupy the complementary pores. This tie in with the weight change of CMS after amine impregnation. Around 3.73% and 5.96% of amine content are discovered respectively in CMS data and CMS taper. These are the obvious evidences of successful amine impregnation. This figure shows the XRD diffractograms of CMS samples. XRD analysis was conducted to investigate the changes in crystalline structure of CMS after amine impregnation. The positions of the crystallinity representing peaks occurred at the same bright angle, 2 theta in the range of 20 to 30 degree, indicating that the crystalline structure of CMS was well preserved even after amination. This suggests that amine functionalization took place in the amorphous region, and it is in complete agreement with other literature. In addition, the intensity of the peak was getting higher. This suggests that the dilution of crystallinity occurred by cooperation of amorphous amine, promoting severe disruption in the crystalline structure of CMS. Both aminated absorbent shows an enhanced performance for CO2 absorption compared to pristine CMS as shown in the graph. As can be observed, the amount of CO2 absorption increased with pressure in all adsorbent. The pure CMS has a CO2 absorption capacity of 2.736 mmol per gram, most likely owing to the carbon microporous structure which offers CO2 adhesion via physical absorption driven by van der Waals force. Amine inclusion has improved CO2 absorption capability to 6.71% at 2.919 mmol per gram for CMS data and 6.17% at 2.905 mmol per gram for CMS taper, due to the interaction of hydrogen bond between N single bond H of amine and C double bond O of carbon dioxide. This proves the contribution of amine toward the enhancement of the CO2 absorption. According to the results, the Langmuir model shows best fit for CO2 absorption onto pristine CMS as shown by the higher coloration R², which is 0.9887 as compared to Fredlich model where R² is 0.9783. This explains that there is only monolayer absorption of CO2 onto CMS. Based on the result obtained, absorption of CO2 using CMS is near to physiosorption rather than chemisorption. The reason behind this phenomenon is that the absorption of CO2 only occurs on the surface of CMS, and the absorption process occurred in a short time. Let me sum up my findings. Through this research, the structural properties of CMS were successfully modified with data and TEPA. The reduction in pore volume, specific surface area, and pore size of aminated CMS were the evidence of amine impregnation. A CO2 absorption test was carried out under 0 to 30 bar to investigate the performance of CMS. The absorption capacity of CMS increased with pressure. It was proven that amine-modified CMS have advantages of higher absorption capacity for acidic CO2 gas. The equilibrium isotherm models of CMS for CO2 absorption were determined. Langmuir isotherm is found to be the best fit. The CO2 adsorption by CMS is a monolayer physical adsorption which occurs in a short time. Although the objectives of this study were all met, the scope of research can be much widened and deepened if more parameters are taken into account. More characterization techniques can be carried out to further analyze the morphological properties of the CMS. For example, Fourier transform infrared spectroscopy (FTIR) can be employed to analyze the composition of organic and inorganic material on CMS. Apart from that, leaching tests should be performed after the adsorption experiment since there is a possibility of amine leaching. Regeneration tests are also recommended to examine the stability of CMS. Thank you for your time and attention. Now I'm happy to answer any question you might have. Bye.